Assalamualaikum warahmatullahi wabarakatuh. Good morning, Pak Adam. Thank you so much for hearing my presentation. I would like to present about biodegradable, colored, anti-static, flame-safer packaging for small electronics. Okay, start with introduction with case overview and design target. For packaging system, foam tray, we use PLA, PBAT, or stretch. For transparent sealing film, we use PLA base. The design target of this packaging is first industrial composable, clear film, bright white or color tray, UV stable, which is they can store the lightning, ESD safe for electronic, mechanical robust, and dimensionally stable, reduce flame spread, smoke, and dripping. For the main problem, the first one is yellowing and gloss loss of film, color fading and dull white tray, foam collapse and warpage, brittleness after hot or humid storage, static shock, dust attraction, ESD failures, rapid ignition, dripping, then smoke, and the last is fragmentation but incomplete biodegradation. The degradation mechanism that occur because of this failure. First is thermal oxidation. What happened in thermal oxidation? It elevated temperature in processing hot storage. Oxygen attacks PLA chain and it free radical form the chain casein, which means a new chemical group, which is carbonyl and peroxide, appear. For the consequence, the molecular weight drops and it causes the brittleness, formation of chromophores, and yellowing. Meltability, it leads to burn smell and black speck gel. And the key takeaway, long residence time in extrusion and hot warehouse storage accelerate this damage. The second one is hydrolysis. What happened in hydrolysis? It because water molecules attack the ester bond in PLA and the chain split into shorter segment and lactic acid. The consequence is it will lead to rapid loss of strength and toughness and increased brittleness and cracking and faster degradation during processing and storage if moisture is present, and humid storage around 40 until 45 degrees Celsius plus stretch hydrophilic dramatically accelerate the hydrolysis. Last but not least is photooxidation with UV degradation. What happened in here? UV light excite the PLA molecules, free radical form even at room temperature, and oxidation continue in the presence of the oxygen. The consequence of this UV degradation is surface embrittlement, yellowing and gloss loss, fading of pigment and inks, and it matters because strong indoor lighting in stores is UV rich. So I think it's one of the causes of the UV degradation in the store. Next is optical change, which is yellowing, color fading, and brightness loss. For the yellowing, it caused by the chromophore formation during oxidation, and it's severe in degradation resin, poorly dried PLA, and UV exposed surface. For color fading, UV breakdown organic pigments and dyes, and polymer surface roughening scatters light, and it leads to wash out look, like in this picture. And then the loss of brightness or white looks gray, because foam cell coarsening change light scattering, and degradation reduce gloss, and moisture uptake alters the refractive index contrast. Next is foam stability, which is nucleation, cell growth, collapse, processing sensitivity. How polymer foams form? It first nucleation, gas bubbles start forming. Cell growth, which is bubbles expand as pressure drops. Stabilization, polymer melts, strength the freeze structure. And why PLA form are unstable? Because low melt strength of PLA, narrow processing of window, hydrolysis reduce the molecular weight, weaker cell walls, and incompatible blend cause uneven stress distribution. And it goes wrong. which is cell merge, leads to non-uniform foam, like in these pictures, walls rupture or collapse, and batch-to-batch variability increase. Next is static build-up. The reason why PLA packaging becomes highly electrostatic because PLA has no mobile charge carries and surface resistivity typically 10 40 until 10 60 ohm per SQ. And what happens? Friction during handling leads to thermoelectric charging, and charge cannot dissipate, leads to static buildup. The effect is shock to workers and dust attraction, ESD damage to electronics. And bioplastic are more often insulating than many fossil plastic, making ESD control harder without additive or coating. Next is incomplete biodegradation, which is fragmentation versus true mineralization. The fragmentation itself is material break into the smaller pieces, still chemically polymer, and can resemble as the microplastic. And true biodegradation or mineralization is microbes convert polymer into CO2, HO2, or hydrogen, carbon, and biomass. Why PLA often fragmented first? Because hydrolysis break chain faster than microbes can metabolize them, and high crystallinity and thick section slow microbial access, and additive can inhibit the microbes. Next is flammability, combustion, dripping, smoke behavior. Why polymer combust, dripping, or smoked? Because heat leads to polymer melts and volatile gas evolve, and gas ignite to flame fits back heat. And PLA specific behavior is low melt viscosity when burning leads to molten dripping, and drip spread fire to new location, and foams ignite faster due to the high surface area. Smoke formation mechanism is incomplete combustion products dense the smoke, and oxygen poor burning in foams worsen the smoke. Next, we're moving to strategy or coherent additive strategy to overcome the failure. The first one, I divided into transparent PLA window film, which is extruded, printed, or sealed, and the tire, the film L, the goals is the best chains at EN13432 plus keep clarity acceptable, and the additive types is minimal AO or it hinder the phenols and phosphite very low dose. And then next is no holes, optional low dose UVA only if needed. ESD mostly by process control, which is ioners, grounding, and optional very mild migratory antistatic. And why it's coherent? Because it keeps the additive low, so the mineralization is less compromised and reduce the gel or black speck by the stabilizing process. But ESD might still fail. Yellowing or gloss loss under UV may persist, but the migratory antiseptic can be haze or bloom. The next one is film M or balanced retail, which is it's the goals is survive the store lighting, keep the clarity, and acceptable composite change. And AO or phenol plus phosphate plus UVA low moderate, consider polymeric less migratory and antistat in bulk or a thin clear antiseptic top coat. And it's coherent because UVA prevents the yellowing polymer antistat or coating, give the more durable ESD without carbon fillers. And the downside is additive may slow composing. Coating must be compost compatible plus addition stable. And the last one is film H or ESD plus shelf life first, which is most robust optic plus ESD durability. And the additive package types is AO plus UVA plus house, carefully haze screening, and clear ESD coating tuned to reach dissipative range. And the best optical stability plus ESD reliability for electronics. The downside is higher risk compose mineralization or certification. Coding chemistry must be validated. Next, the foam tray, PLA PB80 stretch blend, rigid cushioning. The tire is tray L, tray M, balance performance, and tray H, fire plus handling first. The goal is basically to improve the foam consistency without overstabilizing, reduce collapse wrap plus maintaining brightness, improve flame spread, drip plus durability. And the additive package for tray first is AO, bio-based nucleation, plus tight moisturizer control like titanium oxide dispersion, plus UV pigment, no FR or only minimal mineral FR. And it's coherent because the keep composed pathway cleaner improve the morphology and witness mainly via structure, but it leads to warp patch, humidity, brittleness, presses, etc. For the 3M, the additive package is AO plus low dose chain extender like epoxy multifunctional, compatibilizer, PLA, PBAT stretch, nucleation aids, and rutile, titanium oxide plus like fast fitment. And it's coherent because it's chain extender plus compatibilizer improve the melt strength or toughness, and stable foam keeps the bright appearance. Tray assists reduce the dust and shock, but composite mineralization risk increase, and stretch still moisture sensitive must validate the SD and aging. For the last one is improve flame spread drip durability, which is AO chain extender compatibilizer nucleation and into meson, and the coherency is in intermittent char reduce the flame spread and can help smoke foam stability improve. And the downside is it can wreck foam and with whiteness brittleness can increase. Next, after we divide it into two, the next one is we create the gate matrix or decided if it pass or fail quickly. The first one is processing stability gates, which is it prevent gel, black speed, and burn smell. The test is raising moisture before the extrusion, and the passing criteria is typically needs the low moisture and inline dew point and diagnosed by hydrolysis driven degradation and gel. The second one is melt flow or viscosity drift. The criteria is minimal drift after the controlled reheat or extraction, and it diagnosed by thermal or oxidative stability. For film gel count or black speck count, criteria is below visual threshold for window clarity, and it diagnosed by degradation, contamination, and poor filtration. For optical aging gates, which is yellow gloss fade, the test is UV rich exposure, film printed tray, and the condition is UVA or story light simulation plus oxygen, and the pass criteria is low delta B or yellowing, gloss retention, and accept rate haze. And the second one is hot or humid aging with 40 until 45 degree at high RH, and the criteria if passing is no over haze, no major brightness, no cracking or wrapping, and that's is suggested condition and pass criteria. Next is mechanical and dimensional gates in warehouse and shipping. The test is compression or cushion retention in the condition before or after hot cuming aging, and passing criteria is retain protective stiffness and no cell collapse. And then the next second one is wrap measurement with stake load at 45 degree Celsius, and the criteria is wrap with intolerance, no brittle fracture on press test, and the film brittleness or tear after UV plus hot humid. It has to be no cracking at fault or bend and still integrity maintained. And second one is ESD gates or electronic gate safe, which is the test is surface sensitivity and passing criteria is moved from 1050 to displayed range, and the notes confirm the target spec with customer. And the static decay time, the pricing criteria is change decay rapidly, and the attraction handling is visual plus particle adhesion test. The next one is fire safety screening, especially for tray foam. The test is small scale vertical or horizontal burn screen. And what you run is quick go or no go ignition, flame spread, and it tells you to early ranking of your package. And the second one is dripping observation plus mass loss, which is document dripping and secondary ignition and critical for a logistic partner. Smoke density screen or comparative smoke tendency and minerals chart often help. Carbon fillers often worse set. And the last one is composability gates, which is the first one is disintegration, and to test is industrial composite condition, and pass criteria is no visible residue beyond allow limit. Second one is mineralization, carbon evolution versus reference test, and it require percentage within the time frame. And the last one is ecotoxicity, which is compost plant growth plus heavy metal and no adverse effect. Okay, to conclude this whole presentation, the key point is no single biodegradable plastic formulation can meet all the target and it needs to careful compromise. Hence, we need to build minimal but targeted stabilization or not over stabilization. The second one is function separation, which is bulk material versus surface coating. The third one is architectural design, which is multi-layer film, optimized foam morphology. The last one is system level solution, ESD handling controls, and secondary packaging for the fires. Here is my reference. Thank you so much for your attention and have a nice day.